So in this presentation we're going to look at alpha, beta and gamma decay in some detail. So very quick recap: atomic number is the number of protons, mass number, total number of protons plus neutrons. Here's an example: hydrogen 3, it has 1 proton, as you can see, bottom left hand corner, and it has 3 nucleons altogether, 1 proton plus 2 neutrons. So alpha emission, alpha particles, a helium nucleus, 2 protons plus 2 neutrons. There's a large unstable nucleus, for example americium-24195, decaying to neptunium-23793. And you can see the equation there at the bottom. Notice that the 237 and the 4 add up to give 241, and the 93 and the 2 add up to give 95. So here's an example: radium-222 decaying into an isotope of radon by alpha decay. The 2 missing numbers there must add up either side of the arrow with the numbers for helium to balance the equation on the left hand side. So if we look at how this pans out, we can see that the mass number for the radon isotope must be 218, since 218 plus 4 equals 222, and the proton number, or the atomic number at the bottom, 8 must be 86, because 86 plus 2 is equal to 88. So a second example, you've got polonium decaying into lead plus helium, alpha particle of course. So you can see the numbers there. The polonium must have a mass number of 210, because 210 is equal to 206 plus 4, and the atomic number must be 84, which is equal to 82 plus 2. So now looking at beta emission. Beta decay involves the emission of an electron. Beta particles, an electron of course. Note its number 0 minus 1. In beta decay, a neutron within the nucleus decays into a proton plus an electron. The electron is ejected as the beta particle, and the new nucleus will have an additional proton, so in this case going from 6 to 7, and 1 fewer neutron, in this case going from 8 to 7. Notice though that 7 plus 7 and 6 plus 8 are both 14, so the mass number is unchanged. So here's an example of beta emission: iodine-131-53 decaying to xenon isotope. What are the numbers for the xenon? Well, 131 plus the mass number of xenon plus 0, so that's clearly 131, and the atomic number added to minus 1 must give 53. This means that the atomic number of xenon isotope formed in this case through beta decay must be 54. So then finally is gamma radiation, which is in some ways the most straightforward of them all. A gamma radiation is just a photon of electromagnetic radiation. So being massless and chargeless, it doesn't affect the mass or atomic number of the nucleus. So finally, just to discuss what happens to alpha, beta and gamma radiation when they pass through a magnetic or electric field. Types of radiation that are charged are affected by both electric and magnetic fields, but anything that is non-charged will not be. So which of the ionizing radiations are charged, and which of those has the most charge? Well, alpha and beta are charged, but alpha is the most charged. Which type is not deflected at all, and why? Well, of course that would be gamma radiation, because it doesn't have any charge. So in summary, here is what happens when alpha, beta and gamma particles are moving, in this case from left to right, and enter a magnetic field. Notice the magnetic field in this particular orientation is positive at the top and negative at the bottom. Alpha particles, being positive, will be deflected in such a way that they are deflected towards the bottom plate, which is the negative plate. The beta particles will be deflected towards the positive plate. The gamma rays, of course, being uncharged, will pass through undeflected. Note also that the beta particles have a much tighter radius than the alpha, and this of course is because the beta particles are lower mass, so therefore will be more strongly affected by the electric field. And finally we see a similar situation in the case of magnetic fields.